specifications that we have for common collector and show you a little bit about meters, how ohm meters work. First thing we probably need to look at is this guy right here. Now, what's that a symbol for? And we put it in the circuit. How do we bias it? Normally, if you forward bias it acts like a diode. Y'all understand that? Yeah. Okay. And if as long as we operate it below its Zener breakover voltage, it acts just like a silicon diode. But as soon as we get above the breakover voltage, it's going to break over, and the voltage is a lot lower. Now, the problem with the Zener regulated power supply, so normally what we were doing is we were taking our voltage right here. Now, the problem is that Zener can handle very little current. So the power supplies we developed were on milliamps, right? When y'all did y'all's labs, it was in milliamps. So the problem with the Zener is that it cannot handle very much power. Huh? Well, power is the problem. Power is the problem because P is equal to V times I, right? You understand? So when we say it can't handle very much power, right? You understand? Because if we make it handle too much current, it's going to do what? It's going to burn up, right? So what we're going to do now is we're going to come up here and hook this up to a bipolar transistor hooked up as an emitter follower or a common collector. And now we're going to take our output over here. That makes sense. Yeah, because remember, of course, to see this thing work, you're going to have a load out or it won't regulate. We're depending on this 0.7 of a volt, which is pretty constant. It's not exact, but it's pretty constant. That means if my Zener was rated at 8 volts, then right here I would have 7.3 volts. And it can't drop down, right? You understand? Because if it tries to drop down, my Zener is just going to put more current into it. But now, what we're doing is we're providing base current. And what do we get out of common collectors? What's the big gain we get out of common collectors? Current. And that's what we're doing. We use the Zener for our what? Voltage reference. And then we feed the base of the Zener into the Zener voltage into the base of a common collector. By the way, in power supplies, people call this a series pass. They call it a series pass transistor. Can you see why? But what is it hooked up? It's hooked up what? It's hooked up common collector, also called emitter follower. But in power supplies, we call it a series pass. And of course, now, you know, if this guy here's got a minimum beta of, its odds are it's going to have more, but if it has a minimum beta of 30, that means if I put 30 milliamps over here, I'm only going to have to put 1 milliamp over there. Okay? Y'all understand that? Now I can come up, yeah, well, that's what it is. I mean, that's what it is. It's a current amplifier, right? We can come up here and do this. We can hook them up Darlington. So up here I might have like a TIP41, which will do about 6 amps. Down here we might have like a 2N3904. Now here we're going to lose what? Between our output, our regulated output, and our reference voltage. We're going to lose 1.4 volts, but that's no big deal. And then I would come over here and hook this up to my what? My Zener. Now this guy here has a minimum beta of 30. This guy right here has a minimum beta of 32, believe it or not. So what would be my total beta? 900. Y'all understand? 900. Yeah, so now if I got 3 amps over here, 3 amps, now we're talking about 3 amps, right? You understand? How much current would the Zener have to supply? Well, the maximum it would have to be would be 3 amps divided by 900. Odds are it's going to have to provide less because we're using minimum beta. So how much current would the Zener have to supply 3 amps over here, to get 3 amps over here? 3 amps divided by 900, right? What would that be? What's that? Milli? Okay, so 3.3 milli. I thought it would be less than that, but 3.3 milliamps out of control by the Zener, right? You understand? To get what? 3 amps out, which is pretty neat. I wouldn't go more than two stages, and that's the advantage of what we call a Darlington. When we take the base of one and feed it, the emitter of one and feed it right into the base of the other, we call this a Darlington arrangement, right? You okay? Another thing we use these things for, which is really cool, it's a combination of a common emitter and an emitter follower, but we'll look at this. This is the circuit I have hooked up here. By the way, you could get a voltage regulator like a 7805, which is rated at 1 amp. And you needed a high current 5-volt supply, you're only going to lose 0.7 of a volt, which will be well within the limits. I'm trying to draw, guys, but it keeps wanting to do the eraser for me. So I could take a 3-volt, I could take a regulator like this, or like a 7805, which is a 5-volt regulator, right? Fixed regulator. And then I could come over here and hook up to my unregulated side, and then I could come over here and put a series pass right here and hook it up on that right there. So right here I might be able to get 1 amp, but up here this might be a 3055. A 2N3055 is rated at 15 amps, but that's max. Normally on here we're not concerned with the amount of current a transistor can handle, because if a 3055 is rated at 15 amps, what does that usually mean? What region do you think it's operating in to get 15 amps? Saturation. That's exactly right. Because saturation is dissipating its least power, right? So if you're not going to operate a transistor in saturation, then you're looking for that PD rating, that maximum power rating. And that's what you don't want to exceed, right? You understand? So these guys are operated in the active region. So to get 5 volts out, I've got to have maybe 5, 6 volts in, right? I mean, not 6. I got to have more voltage unregulated than I got what? Regulated out, right? So that means they're always going to drop voltage. So if you're going to operate it in the active region, what you got to do is you got to know that you got to figure out your maximum collector current to make sure it does not exceed. Not only does it don't exceed that, but you'll never get that in the active region. Y'all understand? What you're going to do is say, okay, the maximum current I'm going to get through that, what would be the maximum power? And you're going to make sure that it's less than the maximum power rating of the transistor. So in the active region, we're concerned with the what? Power, right? You understand? The maximum power. If I'm using it as a switch, I'm concerned with the maximum current. Y'all understand the difference? Because if we operate in the active region, it's acting like a rheostat. If it drops voltage, if we push current through a voltage drop, what do we get? We get power. And if you exceed the power rating, so you can exceed the power rating on a transistor before you exceed the current rating on the transistor. Everybody understand that? And of course, and this is another reason why we need to know VCE. So what we do to calculate PD is we'll have to know voltage collector to emitter times what? Times IC, and that would give us the power. That makes sense? Everybody okay? And I make sure I need to choose a transistor that can handle that power. And we're concerned when we operate this, we're concerned when we're in the what? Active region. When I'm operating as a switch, And then I'm concerned with IC max, right? Make sure I don't exceed that. If we're operating in cutoff, what am I concerned with? And that's the breakover voltage, right? So when we cut it off, we want to make sure it will block the breakover voltage. When I'm cutting it on, I'm concerned with IC max. If I'm operating it in the active region, I'm concerned with power and the breakover voltage. This guy here is always a concern. Normally, we don't have to worry about if it's operating saturated because it's not dropping hardly any voltages. Okay, so this is kind of like my power supply that I have that I'll bring in eventually if I can ever remember it, that I built from scratch. I built that out of a golf cart charger. I used the transformer and the case and everything out of there. It's getting kind of old, but I'll bring it in the one I use at home. Another thing, the one that I have hooked up here is like this. We had a little project one time, and it wasn't hard. Where somebody was trying to get the same current, no matter how many LEDs they put in series. So what I have up here, I have a 470 ohm resistor. That's the best I could do. And over here, I have a plus 5 volt power supply. Is emitter base forward biased? Yes or no? It's an NPN transistor. Is it forward biased? Do I have the emitter pointing toward common? Yes. Do I have a plus on the base? Okay. So this guy here is going to drop approximately what? 0.7. So what do I have across my 470 ohm resistor? I have 4.3 volts. Right? Understand? Now that's not the trick. The trick is up here. So I'm going to come up here and I'm going to put a diode right here. And I'm going to hook up this directly to plus 12 volts. Now, what would be the current flow through the diode? Somebody give me some guesses. How do I calculate? Well, we're going to assume that IE is equal to IC. Well, I know the voltage drop across IE, and I know the voltage drop, and I know the size of IE, so I can calculate IE, right? Okay, y'all got to, hopefully y'all start picking up on this stuff. So IE would be equal to 4.3 divided by 470 ohms. So IE would be equal to what? This is close to that I was getting. I was shooting 9.1 milliamp or close to it. Okay. So this is what I have set up here. So I've got my 470 ohm resistor here. Here's my 5 volt supply coming in here. Here's my 12 volt supply coming in right here to this diode right there. And my diode's on, and it's conducting 9.1 milliamp, which is well within its limits, right? Okay, guys, what would happen if I come over here and put another LED right here? What would be the current flow through both of them? Huh? Exact same current, because the current is set by this resistor right here. So what happened is the transistor, what I'm going to do is I'm going to show y'all this. Let me turn on my meter. Okay. So what I've got is I'm gonna go back to one diode, and this is voltage collector to emitter. Okay, I'm gonna go back to one diode. I'm at one diode. So now my voltage collector emitter is equal to 10.3 volts. Let me see. Let me put my meter to show you. And I have 12 volts. I guess I got 12. I don't want to move my meter around. I'd have to see how much I've got. Okay. And the other volts is across the other diode. You'll follow this? Okay. Now I'm going to come up here and I'm going to put another diode in series. Now I have two diodes, two LEDs lit, and my voltage collector to emitter automatically drop down to drop the remainder of the voltage. Because the current is not what? It's not changing. I'm going to come up here and hook a third diode in series. Every one of them's lit up the same intensity, no matter how I put in series, and now the voltage drop collector to emitter automatically drop down to 7.1 volts. I'm going to come up here and put another diode in series. The voltage collector to emitter drop down, and all diodes are still lit up. Right, you understand? So what I've set up here is what we call a constant current source. So until I run out of voltage, I can hook how many LEDs in series? Until I run out of voltage from my power supply. So here's one more, okay? Now I've got 1, 2, 3, 4, 5. They're all lit up the same, right? Because it's still 9.1 milliamps. And my voltage drop across my transistor drop down because it's a constant current source, right? You understand? So what my transistor is doing is varying its opposition to keep the same current flowing. Here's the last one. Come up here. See, that's the fourth one. It's dropped down to 1 volt. These guys drop about 1 point something volts apiece. If I put another diode in series, everything's going to fall apart, right? You understand? Because why? I have no more voltage available. All of my source. So this would be a good little project on your car. So this is a constant current source. Another thing I've set up here is I'm gonna disconnect this, and this is the way your meter works, by the way. Now it's not going to be accurate because I couldn't get exactly 10 milliamps. So I've got my meter set up to measure voltage, and what I'm going to do is I'm going to move it across where I'm going to put my resistor at. Oops. I just messed my thing up. Nope, I'm okay. Okay. So what I'm going to do is I'm going to set my power supply to 10 volts, or we'll calibrate it here in a minute. Let's see what I can do. My current is not exactly 10 milliamps. What I'm going to do is I'm going to take a resistor. This is a 330 ohm. And I'm going to put it in 333 ohm. I'm going to put it into my constant current source. And of course, this is not accurate because it's not 10 milliamps. It's 330 ohms, and I'm measuring the voltage drop across the resistor, and it's measuring 3 volts. I'm trying to show you how your ohm meter works. Okay. Now, it's not right because I can't get 10 milliamps, right? You understand? Okay, what I'm going to do is take the 300 ohm out, and I'm going to come up here and put, this is a 10 ohm. My meter is going to measures 0.9. This is a 10 ohm. So if you take this as 0.9, so we're using this right here, so that would be 0.9, 0.09, so that's 10, this is 10 ohms, right? You understand what I'm saying? Okay. This is a 200 ohm. and it's measuring 1.82 for a 200 ohm. So every time I put a different resistor here, it's the output of this thing is trying to give me a constant current. Let me draw the circuit for you so you can know. Oops, wrong one, Rich. So what I've got is I've got the same circuit. I'm putting plus 5 volts here. I'm going through my transistor. $470 ohms. And what I'm doing is, this would be my black lead on my meter. This right here would be my red lead on my meter. And what I'm doing is I'm putting my resistors up there. Now, if this was exactly 10, and of course we have 9.1 milliamps, so mine's not exact. All mine are low, right? You understand? But if I could set this up for exactly 10 milliamps, then my meter would measure volts that I could very easily interpret as what? Ohms. And this is your ohm meter right here. This is what your ohm meters do. So when you switch your meter over to ohms, it turns it into a constant current source. And what it does is we're measuring across the resistor, right, or whatever we're measuring, and the output voltage steps up until it gets a certain amount of current flow. And then the meter interprets that or displays it in what? Is ohms. And this is why when you hook your meter in backwards, you cause problems, because right here is your power supply. And what you're doing, if the voltage is bigger than your power supply, it's going to push voltage back through, it's going to push current back through your own meter, right? You understand that? And now you're pushing current through volts into a system that's not designed to handle a lot of voltage, and it'll burn your own meter up. So this is why you got to be really, really careful when you measure ohms, because you're turning that thing into a source, right? And we know what happens if I hook sources up wrong, we can get problems. So this is, so we just set up using a emitter follower, we set up a constant current source. And this is why it won't check Darlington pairs, because there's not enough voltage out of your meter to cause that constant current to flow through two junctions. That's why we can't check an LED. Because an LED requires more voltage than your meter will do what? Can step that voltage up. So you can't check an LED with an ohm meter. You can't check a Darlington pair with an ohm meter. There's some SCRs you can't check with an ohm meter. Later on we'll show you some SCRs and how you can fire the thing with an ohm meter, but they don't put out enough current to fire your big SCRs. We'll show y'all what y'all can do about that. So these are emitter followers, guys. And what do we get out of an emitter follower or a common collector that makes them so good? We get what kind of gain? Of course, we always get power gain, right? You understand? We get what? Don't get any voltage gain out of a common emitter. Here's my output right here, right? You understand? I mean, emitter follower. Here's my output right here. We take the output on the, so emitter follower, the output is in the emitter circuit. And if I put 5 volts there, I get 4.7 volts right there, period. If I put 8 volts over here, I get 7.3 volts, right? You understand? But I get it at a lot higher current, right? You understand that? Because we get current gain. If we get current gain, we're going to get what? Power gain. Y'all understand that? Yes or no? Because the input voltage and the output voltage are the same. Power is equal to V times I. But you get more current out than you put in, right? You understand? So these guys are real neat. We use them as series pass on linear power supplies. We use them as constant current sources. We use them for Class B amplifiers or AB amplifiers that we looked at last class. So these are the two most popular, of course. So if I want to set a constant current through a load, so this is not a saturated switch, right? You understand? Because this guy right here is going to adjust the voltage drop across the collector to emitter to get how many loads I put in series, the same current. until you run out of this supply right here. Once you drop everything in your circuit in it, once the transistor saturates, then you're through. Because once the transistor saturates, it can't change its voltage drop anymore, right? Constant current sources. Constant current sources, and then power supplies, series passive and linear power supplies. Switching power supplies are different. They use switching power supplies. Your output is switched between saturated and off. They don't operate in the active region. All right, guys. So isn't that neat? So I can come up here and just how many did I put in series? I got 1, 2, 3, 4, 5, 6. About 2 volts per. It's a little less than 2. 2 is a rule of thumb for LEDs. If you don't know, 2 volts per. Usually it's 15 milliamps. 2 volts per 15 milliamps is safe on every LED I know. If you know the part number though of your LED, you need to look up the voltage drops, the VF of them, and also the current flow, right? If you don't know the voltage drop, then 2 volts, VF 2 volts, 15 milliamps is a real good rule of thumb where you won't burn them up, for LEDs. And that's just, these are all common collectors. Emitter follower and a common collector are the same thing. And that's why it's called emitter follower, because the emitter follows the base. So whatever's going on the base is going on the what? The emitter. So a common collector is referred to, it could either be called an emitter follower or a common collector. Those are exactly the same thing. No. The highest current flow in the transistor is what? Emitter. So I can hook loads in the emitter or I can hook loads in the collector. Collector, we can get voltage. Collector, right, you understand, collector is not the highest current. So, so this is a combination right here, okay? So a common emitter, what we do, and the problem with a common emitter is they have to have a high output impedance. If they've got a high output resistance, it means we're limited with the amount of current we can get out of there, right? Y'all understand that? So that means I come over here like this, and I do a common emitter, and let's don't do a voltage divider. What we're going to do is we have to put a resistor in series with the emitter, because a transistor does not control a voltage, it controls a current. So it acts like a rheostat, right? So that means if I'm going to get an output voltage, I've got to put a fixed resistor in series with it. Okay. All right. So I got to put it right there. So this resistor right here, we call it RC, right? I'm going to put right here, this is where VN is coming from. This is where V out is coming from. And my output is developed across that resistor right there. Okay, you understand? A common collector, I take the collector and connect it directly to VCC. There's no resistor in a common collector circuit. Then I come over here and I take my output off the emitter. Okay, you'll understand. So my output comes off right here. So on a common collector, this is out and this is in. So VN is on the base, and we take our output off the emitter. So no, we don't always take our output off the emitter, right? You understand? I mean, off the collector. So this guy here's got to be big, right? You understand? This guy right here don't have to be big. So I can make this a 10 ohm. Right? You understand? There's nothing up here to limit my current. Right? Because we're not developing a voltage drop across the collector. We're developing across the collector. At the collector, we're developing our voltage at the emitter. So that means if I come over here And I can't put 5 volts in. Of course, the maximum I can put over here is 7/10 of a volt, right? Of course, what we do to prevent that is we come up here, we put a resistor there, we put a resistor right here, we put a resistor right there that sets up a constant current for the bias, not for the input, right? You understand? That allows us to get our emitter up to a certain voltage, maybe 2 volts, but now my input is still limited to a maximum of plus a 1 volt peak peak. That's the most I could put into this thing, right? You understand? Unless I get this voltage up right there. How much voltage can I put up in this right here? Let's say I have 20 volts right there. Well, I could put, theoretically, I could put all the way from plus 10 to minus 10. I could bias this right here at 10 volts, and I could put plus 10 or minus 10 in. Like this, though, I could come up here, I could put 20 volts in and get 20 volts out. Now, that's if I had absolutely no voltage drop. So what's nice about a common collector is I can put a real high voltage into it, right? You understand? So what we're saying is that, but I can't get voltage gain out of it. This guy right here, I can get voltage gain out of it. But I can't get a lot of current gain. Why? Because of this dang collector resistor right there. Right? You understand? If I make that collector resistor real small, then the transistor is going to burn up, and plus my power, my amplifier is going to become so inefficient, it's going to be basically a waste of time of even putting one in there. Because what happens with these guys, right, these Class A amplifiers, they have to be biased on all the time, right? Down here, I don't have that collector resistor. So what's limiting my current now? Well, limiting my current is the size of my load, but this right here is the load. Normally, that's the load. We hook the load in the collector. Over here, I'm going to have to put my load where? Well, I can put it right there. That can be my load in a saturated switch. But in an amplifier, my load would probably be out here, right? You understand that? Plus, I can do this with a common collector that I cannot do with a common emitter. And this is what we had hooked up the other night, where I could come in up here and I can use a PNP, an NPN right here. I can come down here and connect a PNP right here, right? And I can hook this up to a positive supply. I could hook this up to a negative supply, and I take my output right there. No coupling capacitors, no anything. So whatever I put on the input, I'm going to get what? On the output. Now we looked at this. Right now we got this crossover distortion. What causes the crossover distortion? That 7/10 of a volt required to turn it. Is this AC or DC out? Huh? This is AC. This guy here gives me the negative alternation. This guy right here gives me the positive alternation. Right? You understand? So we can actually get AC out of these guys. Put AC in them, get AC out, which is pretty neat. But we don't get any voltage gain. But we get the gain of the transistors, right? You understand? So if this thing's got a typical beta of 100, then that means I could get 1 amp out for 100 milliamps in, right? I'm sorry, 10 milliamps in. And this would be a Class B. What's Class B? What's Class A? Yeah, so you get an image of the input is on the output, right? You understand? Everybody understand? Class B is what? 180 degrees. Can't get, we call these Class Bs, but we don't quite get 180. And then Class C, less than 180. Where do we use Class C's at? Huh? What's their domain? Not in audio. Huh? Well, RF, radio frequencies. You say cell phones, but all your TV stations, all those guys where they're running on a carrier, and that carrier's at the same frequency. Then we can use the tank circuit to regenerate the rest of the energy, right? Tank circuits are really, really neat. I don't know if y'all had time to get them in AC, but those guys right there basically consume almost no energy at all, but they store energy. So they store energy out of the Class C when it turns on, and then when the Class C turns off, the tank circuit discharges its energy back into the circuit, which is really neat. So you get a real good, but you have to operate those things at a constant frequency, right? Which is what radios are. So we transmit on a carrier. And what's a carrier? What's modulation? You already know what modulation is. Huh? Yeah, it's when we put information on another frequency, we call a carrier. That's called modulation. So when you place information on a carrier, and that carrier is what the Class C is tuned for, is the carrier. And then we don't have time to get into this, but tank circuits have what we call a bandwidth, which means the frequency can change a little bit, and they're still very, very efficient. So we have a bandwidth. What's a demodulator? Yeah, it lets the frequency come through. And everybody's heard of the term modem. What's a modem? It's a modulator, demodulator in one. So when you send information out and put it on your cable, which is designed for video, right? You understand that. It modulates it, puts it on a carrier. And then when you receive stuff back, what does your modem do? Demodulates it, takes it, strips the carrier off, and gives you information, which is pretty interesting. So yeah, Class C's work great on that. They work great. But they depend on things to be at a precise frequency, right? Y'all understand that? And then so on your cell phone, your antennas are probably Class C when you transmit. All the channels on your cable probably broadcast on Class C's. Or all your ham radio operators, your 2 MHz operators, Class C. CB, if you got to know CB, it was real big for a while. Now everybody uses cell phones. If you want to talk to somebody driving. But this is some of the uses for these things for emitter followers. Not only do we get the big current gains out of them, so we can use them as our outputs for our stereos. We can. This is a combination of a common emitter and a common collector. So that we're using this to get a constant current source, and then we're putting our load in the collector. Let's see what else. But I wanted to show you that with the meter. Ain't that neat? So we're measuring these resistors, but we're not actually measuring resistance. We're measuring what? Voltage, which is pretty cool. All right, guys, go to lab. Then we'll go to, Chase, you might want to get a trainer and split off on yourself. If you want to do that, it'd be fine. We got plenty of trainers. If you work with Wesley, you're going to have to start where he's at, but that's up to you, your call. Yeah, we got plenty of parts. We got plenty of trainers over there. Yeah, that's no big deal. Have 2 hours to take tests. So what does that mean? We'll start it at 7. I got 45 minutes.